Welcome to this learning module, presented by Harvey H. Harper, focusing on retention systems and the BMPFast project. Over the course of this module, we'll explore how retention functions as a critical method for removing pollution. We'll also delve into how simulations were utilized to optimize retention strategies, aiming to achieve an effective average annual removal rate, and examine how this removal effectiveness can vary significantly based on specific watershed characteristics and prevailing rain conditions. In this section, we will delve into retention systems, which are frequently used best management practices for improving water quality. We'll define what these systems are and identify common types classified as retention. You'll also learn how the effectiveness of these systems can vary significantly across Florida, influenced by diverse meteorological conditions and watershed characteristics. Finally, we'll explore practical application by examining the tables within the Applicant's Handbook, Volume 1, and demonstrate how to use them to calculate the annual average removal effectiveness of these systems. We'll begin by defining what we mean by retention in the context of stormwater management. Retention refers to a group of practices where a specific treatment volume of stormwater is completely evacuated, either by infiltrating into the ground or through other methods, within a relatively short time frame, typically less than 72 hours, or sometimes even 3 hours. The key characteristic here is that there is no surface discharge for that treatment volume. This process results in a variable, but often significant, reduction in the overall runoff volume. Some common best management practices, or BMPs, that function as retention include infiltration or retention basins, which are also known as retention ponds. Permeable pavements are another excellent example, as are underground storage or exfiltration systems. Rain gardens and swales can also be designed to provide retention functions. Now, let's contrast that with detention. Detention involves a group of stormwater practices where the treatment volume is held or detained for a period of time before it's released. Unlike retention, detention practices typically discharge the treatment volume over several days, and they do not result in a significant reduction in the overall runoff volume. Essentially, retention captures a fraction of the runoff water, preventing its release, while detention merely holds it temporarily before releasing it downstream. Examples of BMPs that use detention practices include wet detention ponds and detention rain gardens. Here we're looking at some common types of retention systems, often used in stormwater management to help control runoff and improve water quality. These systems are designed to hold water temporarily, allowing it to slowly infiltrate into the ground or be released at a controlled rate. We see examples here of retention basins, which are sometimes designed as rain gardens, along with roadside swales that convey and treat runoff. Exfiltration systems are also pictured, which allow water to seep into the surrounding soil. Finally, we have permeable pavements, an innovative solution that allows water to pass directly through the paved surface rather than running off it. When designing a retention basin system, we often refer to a specific treatment volume, sometimes called a pollution abatement volume. This is the volume of water intended to be treated within the basin. At the elevation marking the top of this treatment volume, you'll typically find a discharge weir, an orifice, or sometimes a combination of both, which controls the outflow from the basin. It's crucial to remember that if you're using a retention system that relies on infiltration to achieve capture credit, the seasonal high water table must be at least 2 feet below the bottom of the infiltration area. This ensures proper functionality and prevents saturation issues. Ultimately, the specific depth and volume of the retention basin are determined by the desired effectiveness and performance goals of the system. Roadside swales are a highly effective tool in stormwater management because they combine both the conveyance of runoff water and its treatment. They are designed to function as linear retention systems, meaning they not only transport water but also encourage it to infiltrate into the ground. To enhance this crucial infiltration volume, various features can be incorporated, such as swale blocks, check dams, or even raised inlets. These elements serve to impound or pond the runoff water for a longer duration, allowing more time for it to soak into the soil beneath. You might see an example of this with a raised inlet, which facilitates water storage directly within the swale, or a raised swale block performing a similar function. It's important to note that swales do have specific design constraints, particularly concerning factors like side slopes and width-to-depth ratios. You can find detailed design specifications for these within the Applicant's Handbook, Volume 1, Appendix O. We're continuing our discussion on roadside swales, and here we see an example of one that was originally equipped with swale blocks. These blocks were designed to retain runoff, and in its intended function, this swale effectively prevented a significant portion of the roadway runoff from directly entering the nearby lake, thus protecting water quality. What this slide highlights, particularly in the accompanying visuals, is the result of what were termed drainage improvements. These modifications essentially converted the swale from a system designed for retention into an overland flow system that eliminated most of its runoff retention capacity. As a consequence, materials like leaves, which were previously captured within the swale, now directly discharge into the lake. We can see evidence of this in the raised swale blocks and inlets that are now completely blocked with leaves, demonstrating how the system has been altered to facilitate rapid, unimpeded flow rather than retention. This slide focuses on an evaluation of grassed swale performance efficiency conducted between 1982 and 1983. In this study, a water source was deliberately spiked with various nutrients and metals, and then pumped into the swale. As this water flowed down the length of the swale, researchers collected samples and flow data to analyze its effectiveness. It's important to understand that swales have been utilized for stormwater conveyance and infiltration along roadsides for well over 4 decades, and their annual removal capacity can be quantified as retention. To receive annual removal credit as a retention system, the seasonal high water table must be situated at least 2 feet below the bottom of the swale. Furthermore, as noted by Wanyalista and Yusuf in 1993, a reduction in contaminant concentration is directly linked to the residence time of the water within the swale. Generally, a significant concentration reduction is observed when the longitudinal slope of the swale is kept at less than 1%, meaning a drop of no more than 1 foot over 100 feet. Here we see an example of concentration measurements for metals taken along a swale. This particular data comes from the Maitland Boulevard site, where the soils are sandy and dry, and the primary vegetation is bahia grass. On the date this data was collected, January 24, 1983, the flow velocity measured 2.58 meters per minute, or 0.14 feet per second, with a hydraulic depth of 0.038 meters, which is about 1.5 inches. The key takeaway from this kind of analysis is that for metals, changes in concentration are notably enhanced when the flow velocities are lower and when the water has a longer residence time within the swale. It's worth noting that while some concentration changes are observed for most pollutant measures, these significant changes are primarily seen only at slopes less than 1%, or approximately 1 foot of drop per 100 feet of swale length. Permeable pavement is an engineered system designed to allow stormwater to infiltrate directly through the paved surface, rather than creating runoff. The surface course, which you'd see as the top layer, is commonly constructed using either pervious concrete or permeable asphalt paving. This layer typically consists of a 1/2 inch to 3/4 inch aggregate mix and ranges from 2.5 to 4 inches in thickness. Beneath the surface course, we have a filter course. This layer is usually about 2 inches thick and uses a 1/2 inch aggregate, primarily to prevent finer particles from the surface from clogging the lower layers. Below that is the crucial reservoir base course. This layer incorporates larger aggregate, typically 1 to 2 inches in size, and its void volume is specifically designed to provide the necessary retention volume for stormwater. The precise thickness of this base course is determined by the total storage capacity required for a particular site. It's important to understand that the entire storage volume, often referred to as the reservoir, actually encompasses the porosity within the surface course itself, the void space in the filter media, and the significant void spaces within this reservoir base course. When designing these systems, we must also consider that void space is typically reduced over time due to sediment accumulation. Therefore, for practical design purposes, Particularly in tools like BMPFast, engineers often account for what are called sustainable void spaces, which are estimated at about 75% of the initial dry or laboratory void space to reflect real-world performance. Finally, beneath all these layers lies the existing soil. It's critical that this soil undergoes minimal compaction during construction to ensure its natural porosity and permeability are retained, allowing the infiltrated water to further percolate into the ground. Here we're looking at various types of permeable pavement retention options. These include permeable pavers, permeable planters, grassed parking areas, and even site-constructed permeable concrete and asphalt. The key idea behind all these options is to manage stormwater runoff directly at the source. As the slide indicates, most of these are designed for smaller areas and are typically applied on a parcel-by-parcel basis, with the goal of further reducing the volume of runoff delivered downstream. It's crucial for effective stormwater management that we have ways to incorporate these types of options into assessment software, similar to how BMPFast does, to accurately model their impact. It's also worth noting that in certain geological areas, particularly where a swale bottom might be situated near very permeable ground rock like limestone, the recovery of the design treatment volume can be exceptionally fast. This rapid infiltration significantly increases the effectiveness of these systems for the same design treatment volume. However, a critical caveat to this is that in these very same areas, fast-moving waters can unfortunately lead to the formation of sinkholes, which is a risk that must always be considered in design and implementation. Our discussion of retention modeling methods begins with a significant evaluation conducted by Harper and Baker in 2007 for the Florida Department of Environmental Protection, or FDEP. Their work assessed the efficiency of various retention practices. This evaluation was based on a continuous simulation of runoff generated from a hypothetical 1-acre site, utilizing the well-known SCS curve number methodology. For their analysis of capture, Harper and Baker varied several key parameters. They simulated DCIA percentages, that's directly connected impervious area, ranging from 0 to 100% in 5-unit intervals. They also varied non-DCIA curve numbers, from 30 to 98 again in 5-unit intervals. This was all performed for each of Florida's 5 distinct meteorological rain regions. To achieve this, runoff was calculated using continuous historical rainfall data sets from all 45 hourly meteorological sites across Florida. Generally, each site provided between 30 and 50 years of data for the simulations. The comprehensive results of this extensive simulation, covering all these variables and rain zones, are detailed in the applicant's handbook, Volume 1, Appendix O, which was updated in 2024. When modeling efficiency for annual capture, our analysis makes several key assumptions. Primarily, we assume that the efficiency of an infiltration or retention practice is directly related to the portion of the annual runoff volume that is retained. This means, for instance, if 50% of the annual runoff volume is successfully held, we then assume that 50% of pollutants like total nitrogen and total phosphorus are also removed. This approach treats the volume retained as equivalent to the mass of pollutants retained, operating under an annual average condition where minimal variability is assumed. For simplification, the model assumes there's no change in runoff concentrations during a specific event, and it also ignores any groundwater loading. To calculate performance efficiency, we use a continuous simulation approach. This involves modeling runoff inputs into a retention basin based on individual rainfall events over the entire available rainfall record, utilizing data from all 45 hourly meteorological stations. Once runoff enters the pond, further assumptions are made regarding removal efficiency. For any rain event where the runoff volume is less than the designated treatment volume of the basin, we assume a 100% removal efficiency. However, for rain events where the runoff volume exceeds the treatment volume, the assumption shifts. We consider 100% removal for inputs only up to that defined treatment volume. Any runoff that is in excess of the treatment volume is assumed to bypass the pond with 0% removal. Continuing with our efficiency modeling assumptions, we consider a hypothetical drawdown curve that guides the evacuation of water from the basin. This curve is based on common requirements for how quickly water should be removed, specifically assuming a 50% recovery of the treatment volume within 24 hours and a complete 100% recovery within 72 hours. Another key assumption in our modeling is that there's no significant first flush effect from the watershed. While very small watersheds, typically less than 5 to 10 acres, might exhibit a first flush for certain rain events, there's no consistent evidence that larger watersheds experience these effects on a continuous basis, nor is there consistent research to broadly support this concept. Field data has shown that the first flush effect is not as prevalent or predictable as sometimes assumed. Ultimately, we define pond efficiency as being equal to the fraction of the annual runoff volume that is successfully infiltrated. To calculate this annual capture, separate model runs were conducted for the entire period of rainfall record at each of our 45 hourly meteorological sites. The comprehensive data gathered from these sites was then summarized according to its respective meteorological zone. Here we're looking at the modeled retention removal efficiencies, with the source cited as Harper and Baker, 2007. From their Appendix D, these tables were specifically generated to show retention efficiency for each meteorological zone, across rainfall intervals from 0.25 to 4.0 inches in 0.25-inch increments. This results in 16 separate tables per zone, totaling 80 tables altogether. These tables are also listed in the Applicant's Handbook, Volume 1, Appendix O, from 2024. A critical point to remember is that for each table you must interpolate between the CN and DCIA values if they are not in units of 5, and you'll also need to interpolate between tables if the removal treatment depth doesn't precisely match the inches being evaluated. Fortunately, specialized software can greatly assist with these interpolation tasks. Let's look at some key observations regarding the effectiveness of online retention, specifically for a treatment depth of 0.50 inches applied over the watershed. Our simulations have shown that the annual percent removal or capture efficiency is directly impacted by changes in the directly connected impervious area, or DCIA, and the curve number for non-DCIA areas. We observe that efficiency decreases under two main conditions: first, as the DCIA increases, and second, as the non-DCIA curve number value increases. Conversely, efficiency improves as the DCIA decreases and as the non-DCIA curve number value decreases. To elaborate, when the non-DCIA curve number increases, the annual percent removal consistently decreases, regardless of the DCIA conditions. Similarly, if we hold the non-DCIA curve number constant and increase the DCIA, we also see a reduction in the overall capture. This demonstrates the critical role these factors play in determining the annual average effectiveness of our retention strategies. When we examine the impacts of accelerating the drawdown process, we observe some notable changes in retention efficiencies. Specifically, doubling the rate of recovery, such as reducing the recovery time from 72 down to 36 hours, can increase the retention effectiveness by up to about 3.5%. Conversely, if we increase the drawdown time from 36 hours back to 72 hours, we see a corresponding decrease in treatment efficiency of up to about 3.5%. It's crucial to understand, however, that this change in removal efficiency is not universal. At higher treatment depths, particularly as we approach 4 inches, the observable change in removal efficiency becomes quite minimal, essentially approaching zero. Here, we're examining the regional variability in the treatment efficiency of retention systems. We're specifically comparing two common design approaches: the treatment of runoff from a 0.5-inch event versus the treatment of runoff generated by a 1-inch rainfall event. These comparisons are made under specific land use characteristics, namely a 40% directly connected impervious area and a non-DCIA curve number of 70. What we observe is that the performance efficiency of these retention systems is not uniform. it varies significantly throughout the state. This data, for instance, reflects the annual effectiveness for a specific watershed across all 5 rain zones, illustrating how even with identical retention design conditions, there's a notable difference in performance from one rain zone to another. When we compare the 2 design criteria, we find that designs based on treating 0.5 inches of runoff generally provide better annual mass removal than those based on treating the runoff from 1 inch of rainfall. However, the critical conclusion here is that for these particular land use characteristics, neither design criterion, whether it's retention of 0.5 inches of runoff or runoff from a 1-inch rainfall, manages to meet the common performance standard of an 80% treatment removal. This highlights a significant challenge in achieving target removal efficiencies under these conditions. Here, we're looking at the retention depth needed to achieve 80% pollutant removal. Comparing 2 different locations within the state, Melbourne on the east central coast and Pensacola, located in the western coastal area, what we observe is that for the same project design, Pensacola would require a significantly larger retention depth than a project constructed in Melbourne. This difference arises primarily due to the distinct rainfall characteristics in each region. The varying rainfall patterns directly influence the effectiveness of retention systems, meaning that to achieve the same 80% removal target, the system must be designed with greater depth in areas like Pensacola to account for these differences. Here we're examining the retention depth required to achieve a 95% mass removal of pollutants. This figure is based on statewide average rainfall conditions. To calculate this depth, we need to understand the watershed's curve number, or CN, and its directly connected impervious area, or DCIA, characteristics. We're presenting this information so you can compare the requirements for 95% removal against the more common 80% removal specification. It's important to note that achieving this higher 95% removal typically demands a significantly larger depth of treatment. The BMPFast model calculates runoff using specific tabular relationships for annual retention efficiency. These relationships were developed by Harper and Baker in 2007, detailed in Appendix D, and also found in Appendix O of the Applicant's Handbook Volume 1. To perform these calculations, several key pieces of input data are required. You'll need to identify the rainfall meteorological zone for your area using a rainfall zone map, determine the annual rainfall depth from isopleth maps, and define the project's directly connected impervious area, or DCIA. Additionally, you'll need the curve number for the non-DCIA areas, and specify either the retention performance efficiency that is currently provided or the desired performance efficiency you aim to achieve. BMPFast's primary function is to conduct complex interpolations both within and between these reference tables, helping to derive the appropriate retention efficiencies for your specific conditions. Utilizing software packages like BMPFast significantly reduces the time it takes to perform these detailed calculations and helps ensure their accuracy, provided, of course, that the input data you supply accurately reflects the watershed and rainfall conditions of your project. To summarize what we've learned, retention systems are designed to either hold runoff water completely or prevent a significant fraction of the yearly water from being discharged from a surface. It's important to remember that the efficiencies of these retention systems can vary considerably across the state of Florida, primarily due to differences in meteorological characteristics. For calculating the annual average removal effectiveness of these systems, you'll find dedicated tables within Volume 1 of the 2024 Applicant's Handbook. Additionally, there is specialized software available that can greatly assist in performing these calculations accurately and in a timely manner. This module, presented by Harvey H. Harper, has established important research results that aid in the calculation of average annual removal. I encourage you to continue with the next learning modules, which will address how software, specifically BMPFast, can help in performing these calculations in a timely and accurate way for permit applications. This concludes our presentation. Thank you for your time.